Okay, good afternoon, everyone. So, yeah, we'll start now. Okay, good afternoon, everyone. So, myself, Kartiga. So, I am a research scholar from IIT Hyderabad. So, I am handling the problem solving session for this NPTEL course. So, the course name is Fluid and Particle Mechanics. So, course code is given over here, and the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. So this fluid and particle mechanics is a 12 weeks course, and course layout is structured in such a way that for the first half it is like mostly on fluid dynamics and in terms of introduction to Navier-Stokes equation, exact solution, Taylor-Couette flow, rheology, and dimensional analysis, turbulent flow, friction losses, Moody's chart, boundary layer, followed by particle mechanics, like in terms of introduction to particles, their characterization, particulate phenomena, motion of particles in a fluid, in terms of terminal velocity, particle separation, sedimentation of dilute, concentrated, flocculated dispersions, packed and fluidized beds, and filtration. So for books and references, we have the first and foremost unit operations of chemical engineering uh, by McCap Smith, and fluid mechanics by Frank M. White, and introduction to particle technology, and a few references. First one is Schools and Richardson's chemical engineering, fluid mechanics by Piyush K. Kundu, and principles of colloid and surface chemistry by Paul Hemans and Rajagopalan, and last transport phenomena by Bird, Stuart Lightfoot. So, basically, to give you an idea of what these sessions will be, so we will be solving problems related to that week's assignment, so which will help you in submitting the assignments. And if you have any doubts in these problems, you can ask. And also these sessions will be videos are being recorded for these sessions, so which will be made available to you, and presentations will also be shared with you. So if you have any doubts in during this during the session, you can ask me. So the session is from 3 p.m. to 5 p.m. So it is a 2 hour session. So yeah, now in we are in week 2, so we will be solving problems related to this week. And as you all know, like assignments submissions also carry a certain weightage in the final marks. So if you are appearing for exams, be sure to submit your assignments on time. So that's it. We'll now move to the problems now. So first one is a problem where we have this particular figure for the reference. As we are able to see that there is a block which is inclined, which is moving along inclined plane. So the plane is making an angle theta, and the block is moving with velocity v, and the contact area is A, and the liquid film has thickness h. So when we see the statement, what we have is a block of weight W slides down an inclined plane while lubricated by a thin film of oil as shown in figure 1. So this is figure 1. The film contact area is A and its thickness is H. Assuming a linear velocity distribution in the film, derive an expression for the terminal velocity v of the block. If the terminal velocity of the block is 12 meter per second, mass of the block is 7 kg, and area is 45 centimeter square, and the film is 0.5 mm thick, oil of viscosity 0.33 kg per meter second, and density is 900 kg per meter cube. What is the inclination of the plane theta? Report the answer in degrees. So we are just given all the information and we are asked to find what is the inclination of the plane. So as we have seen that here we have a plane. Imagine we are keeping some slide. So in that slide, a block is moving. The particular block has a weight W. It is like having a contact area with the plane. That particular contact area is A. So here the inclined plane, I mean it is lubricated by a thin film of oil. So we have a thin film of oil as we are able to see, and it is the oil film and its thickness is H. H is given as 0.5 mm in the question, and the viscosity of the oil is given as 0.33 kg per meter second, and density is given as 900 kg per meter cube. So we are allowing a block to slide down up an inclined plane, and it is lubricated with the help of an oil, and we are given all the information with respect to how it is moving. That is, the block is having a certain mass, that is 7 kg, and it is moving with a certain velocity 12 meter per second, that is terminal velocity. So the block has attained a terminal velocity. What is terminal velocity over here? It is having a constant velocity. So acceleration becomes 0. And I mean it has attained that steady terminal velocity. And also when we are seeing about the oil film, we know the thickness of the oil film and we know the properties of the oil. That is, we know the viscosity and its density. Viscosity is given as 0.33 kg per meter second and density is given as 900 kg per meter cube. So now we are asked to find the inclination of the plane theta, and we are asked to report the answer in degrees. So that is the question, and now we will see how to solve the problem. So when we are talking about the block sliding, we need to do the force resolution. So we have two forces acting over here, the one in terms of gravitational force and the one in terms of viscous force. So if we balance those two forces, we will be getting the answer. So now we will go. So first let us see what is given in the question, and we are given a block of weight W slides down an inclined plane while lubricated by a thin film of oil. So this lubrication basically resists the motion by giving the viscous shear. So and also the terminal velocity V is given as 12 meter per second, and mass of the block is 7 kg, and area, the contact area between them is given as 45 centimeter square, which is nothing but 45 into 10 power minus 4 meter square, and we have the film thickness as 0.5 mm, which is 0.5 into 10 power minus 3 meter. And also we are given oil properties. The viscosity of the oil mu is 0.33 kg per meter second, and density of oil is given as rho into 900 kg per meter cube. Sorry, rho equal to 900 kg per meter cube, and as we all know, G value is 9.81 meter per second square. So now what we need to find? We need to find the inclination angle, the angle with which the the plane is making. The inclined plane is making a certain angle with the ground. We need to find that angle. So inclination of the plane, that is theta. So now what we are going to do is, we are going to do the forces acting on the block. So it is like we are just balancing the force. So gravitational force is equal to the viscous force, and gravitational force Fg is given by m into g. So we need to find basically it is mg, but here since it is at making an certain angle, we are just resolving the gravitational components and we are getting it as mg sine theta. So now we need to find the shear force, that is viscous force. Viscous shear force, F viscous, let us denote it by F viscous, is equal to tau into E. So here viscous force is equal to tau into A, and this particular tau is the shear stress. Shear stress is given by mu dV by dx, as we all know. So here we are giving it as mu V by H. So here V is the terminal velocity and H is the film thickness. Here it is also we should be I mean in the question it is again given that it is maintaining a linear velocity distribution. So we are taking this. So F viscous is equal to mu into V by H into A. So now we are just balancing this at terminal velocity. So the net force is 0. So that's why we are balancing these two forces acting on the block, and we are substituting everything mg sine theta equal to mu into V by H into A. Okay. So now continuing with that, mg sine theta is equal to mu into V by H into A. So we now know all the values, that is m we know as 7 kg, g we know, and theta is unknown, and mu we know 0.33, v is 25 I guess, h is 0.5 mm, a is 45 centimeter square. So we are just substituting all the known values in the in this particular term. So before we are just keeping the sine theta in one side and taking rest of the terms to the other side. So sine theta is equal to mu into VA divided by H into M into G. So we are taking this mg from here and putting it in the denominator in the other side. So we are getting the value for sine theta. So now we are substituting everything over here. Okay, V is 12 meter per second, not 25. So yeah, was it given correctly in the question? Yeah, V is correctly given as 12 meter per second only. Just a small confusion on my part. So now we are substituting everything, that is mu is 0.33, V is 12, A is 45 into 10 power minus 4 meter square, because it was given in centimeter square, we are converting it into meter square, divided by H is 0.5 into 10 power minus 3 meter, and M is 7 kg, G is 9.81. So whenever we are solving any problems, it is better we solve it in SI units, unless it is an empirical relation or something and we are required to solve in that particular unit system. In other cases, it is better to keep every unit in SI units, so we will be consistent with the units and there will not there will be no issues arising due to units inconsistency. So now after substituting, we are getting sine theta as 0.519. So now since sine theta is 0.519, we need to know the theta. So we are taking sine inverse, and so theta is equal to sine inverse of point. Okay, sorry. Should be. Why did it come 0.587? 519. I'll just check once. Sine inverse of 0.519. Yeah, sine inverse of 0.519. If you have scientific calculator, you can just substitute it there and you will get it in degrees. So again, in the question it was asked to report the answer in degrees. So we are reporting the answer in degrees, 31.26 degrees. So again, whenever you are using scientific calculator, make sure the unit for degrees is in, angle is in degrees and not radians. So if it is in radians, again you need to be converting it. It won't be any other issue. So that is for this problem. So what we did, we have a block of a certain mass sliding down a inclined plane. So we have a lubrication in terms of a lubricating oil, and we know the properties of the oil. So also it is given that there is a linear velocity gradient. Yeah, sorry. Linear velocity distribution in the film. So on that basis, so we are just solving for the forces. So here we are getting viscous shear force and the gravitational force acting on the block. So we know the gravitational force as F is equal to mgx, and here it is mg sine theta, and the uh, viscous shear force we are getting it as F is equal to tau into A. So tau is the shear stress. So shear stress is mu into dV by dx. So here we are denoting it as mu into V by h. So we know V as the velocity and h as the film thickness. So we are substituting again the known values in the equation, and we are getting the final answer, that is mg sin theta is equal to mu V by h into A, and we know all the values except sine theta. So sine theta we keep and we substitute everything, and we get the value as 0.519, and theta is equal to sine inverse of 0.519. So we get theta as 31.26 degrees. So make sure the answer is in degrees, because in the question it was clearly specified to find the answer in degrees. So that is for question 1. Now I hope question 1 is very clear. So now we will go to question 2. So again in question 2, what do we have? We have a moving wall and we have a fixed slipper block, and the height difference between these two is h0 at one instance and h1 at the outlet. So at the inlet it is h0 and at the outlet it is h1. So it is oil inlet and oil outlet. So here it is moving and here it is a fixed block. So now what is given in the question, we will just read. So and the wall is moving at a velocity u. That is also we need to check. So in the question it is given that the fluid flow in a lubrication film can be understood by analyzing the Navier-Stokes equation, but under certain approximation. For example, figure 2, that is this particular figure, shows the part of a region where a fluid is sandwiched between a moving wall with velocity u, that is the bottom, and the fixed slipper block at the top. Let the lubricating oil is viscous and has a density of rho and viscosity of mu. Unlike the previous problem, here the height of the oil film is not constant. In the previous film, the height of the oil film was constant, whereas it is varying between h0 and h1. So h is a function of x. So at x is equal to, if it is 0, we have h0, and x is equal to some height, something, we have h1. So unlike the previous problem, here the height of the film, that is hx, is not a constant. It is varying with respect to x distance. However, if the gap is thin, that is if the gap we are considering is very thin, that is h is very less than L, it can be shown that the pressure and the velocity distributions are of the form P is equal to a function of x and u is equal to function of y, and u velocity is function of y, and v and w components velocity are 0. Neglecting gravity, reduce the Navier-Stokes equation to a single differential equation for u as a function of y. What boundary conditions will you use to solve the problem? Here h is equal to h of x. So the question, I hope it is clear. So we have a moving wall at the bottom and we have a fixed block at the top. So the height difference, fluid is sandwiched between these two. That is the moving wall and the fixed block. So here the height is not the same, but rather it is varying. So at this height it is h, I mean this exposition height is h naught, and at this exposition height is h1. And the gap, if it is very thin, it can be shown that the pressure and the velocity, I mean h is very very small when compared to the total length. It can be shown that the pressure is a function of x and velocity is a function of y. That is, velocity is varying with respect to height, and pressure is varying along this position. And v and w components of the velocity are 0. Neglecting gravity, reduce the Navier-Stokes equation to a single differential equation of y. So we are asked to reduce the equation, Navier-Stokes equation, and we are asked what boundary condition we will be using to solve the problem. So that is the question. It is a kind of a theory question. So we will see how to solve the problem. First, we are just, since it is like a theory problem, we are just going to see the method. So first let us see what is given in the question one more time. Density of the viscous fluid is given, that is rho, and density of viscous fluid is given as rho, and dynamic viscosity of viscous fluid is given as mu. Bottom wall is moving at a velocity u, and top wall is stationary. And film thickness is given as h, which is a function of x. So it is a hx. It is a function of x, and it is very small when compared to the total length. And flow is steady and incompressible. No pressure gradient in the y direction. Pressure is varying with respect to the x direction. Flow is a two-dimensional flow almost, since like no variation is considered in the z direction, and we are asked to neglect the gravity. So now u is given as a function of y. Velocity is varying with respect to the y direction, that is height. And v and w components of the velocities are 0. So there is no flow in the vertical or out of plane directions. And it is given that p is a function of x. Pressure varies in the x direction. So gradients are dominant in the x direction. So now we are asked to find, what are we asked to find? We are asked to just derive the velocity distribution, that is u as a function of y in the lubrication film. I mean, it is not exactly lubrication film, the fluid film, where the height is varying with x, and we start with the Navier-Stokes equation and we apply the approximations. We will start with Navier-Stokes equations and apply the approximations. Okay, so first one, let us just solve for the continuity equation. So continuity equation, here it is an incompressible flow problem, so it is given in the question. So dou u by dou, and it is a two-dimensional problem, so it is a dou u by dou x plus dou v by dou y equal to 0. So are we satisfying the continuity equation? Yes, because v velocity is 0. U velocity is a function of y. It is not varying with respect to x. So it becomes 0. So continuity equation is satisfied. I hope it is understood. U is a function of y. So first term becomes 0. And v is the function, I mean v is already 0. So this term also becomes 0. Continuity equation is satisfied. Now Navier-Stokes equation in the x direction. So it is rho into u into dou u by dou x plus v into dou u by dou y equal to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square. So here we need to see u is there, but again u is not varying with respect to x, so this term becomes 0, and u is varying with respect to y, but v is 0, so whole term in the LHS side becomes 0. So this term, these two terms becomes 0 and equal to minus dou p by dou x plus mu into dou square u by dou x square. Again u is not varying with respect to x, so this term becomes 0 plus dou square u by dou y square. So this term remains. So that is how we get the next step. U is a function of y and v and w components of velocity are 0, and so like applying these approximations we will get this equation, because whole term becomes 0 and this term remains, and these two terms, the first one becomes 0 and second one alone remains. So it is minus dou p by dou x plus mu into dou square u by dou y square. So we are taking this term to the other side, mu into dou square u by dou y square equal to 1 by mu dou p by dou x. So this is the equation wherein we are stating that u is a function of y and it is with respect to pressure. I mean the equation we are getting with respect to pressure. Pressure variation in the x direction as given in the question. So this is the equation which we are asked to obtain. So now what are all the boundary conditions which we will be applying? We will apply two boundary conditions. U at U at the base, that is the bottom wall, is moving with respect to 0. Bottom wall is moving with the velocity u. I mean capital U. So u at 0. 0 is height. If we go and look at the figure, we will be more clear. U at bottom, that is u at 0, height 0, y equal to 0. It is u, capital U. Whereas it is a fixed slipper block. So on applying the no slip condition, we will be saying that here it is 0. So u at some height h of y equal to 0. So those are the two boundary conditions which we will apply. U at height 0 is u, and u at height of y equal to, u at 0 is u and u at height of y equal to 0. This is nothing but the area which is closer to the walls. Near the fixed block. So now we are clear with this, right? So now what, again a quick repetition of what we have done. So we saw what are all the things that was asked in the question, and we just did only two things. First, this continuity equation, we just checked whether it was satisfying or not, and based on that we got to know that continuity equation was satisfied, and we substituted we wrote the Navier-Stokes equation in the x direction, and we know that x component velocity is a function of height, and y and z components velocity are 0. So we wrote the Navier-Stokes equation in the x direction and simplified all the terms in it, and we arrived at the final equation. This equation, if we are integrating and applying the given below boundary conditions, we will be getting the exact equation for u as a function of y. So but now it is a second order differential equation. Dou square u by dou y square is equal to 1 by mu dou p by dou x. So here the boundary conditions given are u as at height 0 is capital U, and u at height closer to the fixed block is again 0, and if that is in the question. So yeah, that is for question 2. Now we will go to question 3. So before moving to the question 3, we have a problem statement based on which we will have subsequent problems. So first one, it is nothing but it is just a one single statement. Consider this simple incompressible plane flow pattern. U is equal to capital U and V equal to 0, W equal to capital W. So capital U and capital W are constants. So what are we given? We are given a simple incompressible plane flow and it is U small, that is x component velocity is capital U, y component velocity is 0 and w component velocity is capital W. So here U and W are constants. So it is a flow is a constant flow problem, constant velocity problem. So now we will see what is given in the questions. So when we go to questions, first it is question 3. Convert these velocities into cylindrical coordinates. Coordinate u theta. Theta defined from the x direction. Okay. This is not. I just changed the existing question, so it is looking like that. Not the thing. So now what are we asked to do? Convert these velocities into cylindrical coordinates u theta. Give me just a minute. My laptop is kind of heating ahead. So yeah, my laptop is quite heating. That's why. Okay, convert these velocities into cylindrical coordinates u theta. U theta options given for this particular questions. We are given few options. First one, u theta is equal to minus of capital U into sine theta. Option B, u theta is equal to capital W into sine theta. Option C, u theta is equal to U into cos theta. Option D, u theta is equal to W into cos theta. So now we have to identify the answer from these. So answer is actually u theta is equal to minus of capital U into sine theta. That is option A is the right answer. So we will just see how to get that answer. So what was given in the question? In the question it was mentioned that incompressible flow and U x component velocity equal to capital U and y component velocity is 0 and z component velocity is capital W. So based on that we are asked to convert the velocity into cylindrical coordinates, that is r, theta and z. That is the cylindrical coordinates. So now we will see. Yeah. So question 3 answer. A simple steady incompressible three-dimensional flow field given by U equal to capital U constant in the x direction, V equal to 0 no flow in the y direction and W equal to W, that is capital W, constant in the z direction. U and W are constants. So now we are just first writing for the continuity equation. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So here since u and w are constants, continuity equation gets automatically satisfied because constants we can't, if we take the derivative it will be 0. So satisfied. Now let us, that is just for the information. It is not required to check it over here also because in the question it was directly asked for the velocities in the cylindrical coordinates. So in cylindrical coordinates, x is equal, generally how do we write? X is equal to r cos theta, y is equal to r sin theta, and z is equal to z. So generally we do that thing only. So velocity components in cylindrical coordinates are ur, it is radial, u theta, it is azimuthal, and uz axial, same as w. So now we are just transforming from the Cartesian coordinates given in the question. We are transforming it into the cylindrical coordinates. So how do we do the transformation? UR is equal to U cos theta plus V sin theta. And U theta is equal to minus U sin theta plus V cos theta. UZ is equal to W. So now here if we substitute for u, v and w, we will be getting this is the general transformation from Cartesian to cylindrical coordinates, and we are now substituting the known values given in the question, that is u equal to capital U and w equal to capital W. So here ur becomes u cos theta, u we are substituting, v becomes 0, so it is u cos theta, and u theta is equal to minus of u into sin theta, again v becomes 0, and uz is equal to w. So that is how we transform from the Cartesian coordinates to cylindrical coordinates. So if we directly jump to this particular step, it is fine. So what was given in the question? We are given that u equal to capital U, w equal to capital W. So now we are asked to convert from the Cartesian coordinates to the cylindrical coordinates. So the transformation from Cartesian to cylindrical coordinates is done through these particular three things. UR is equal to U cos theta plus V sin theta. U theta is equal to minus of U sin theta plus V cos theta. UZ is equal to W. So we substitute all the known values in it and we get the final answer. So here it was asked for in the question to find U theta. So u theta is equal to minus of capital U into sin theta. So that is how we get the answer. So that is for question 3. Now we will go to question 4. In question 4 it is given that show that new components UR, U theta and UZ satisfy the continuity equation in cylindrical coordinates. So what are we asked to? I think, okay, we didn't do directly, but we did for in the Cartesian coordinates. Cartesian coordinates we did in the last problem itself. Even though it was not required in the question, we did it. So similarly, what is asked in question 4 that show that new components UR, U theta and UZ satisfy the continuity equation in cylindrical coordinates. So it is a very straightforward problem. We are just asked to show it is satisfying the continuity equation in the newly transformed coordinates. So first, let us write given u equal to capital U, v equal to 0 and w equal to capital W. So in the newly transformed coordinates, ur becomes u cos theta, u theta becomes minus of u sin theta and uz becomes w. So that is the things which after transformation in how it looks like. So in the question 4 we are asked to we are asked to prove or we are asked to show that the velocity components in the newly transformed coordinates satisfy the continuity equation. So now we need to write the continuity equation in the cylindrical coordinates. So for that continuity equation in the cylindrical coordinates for the incompressible steady flow problem, 1 by r into dou by dou r of r into ur plus 1 by r of dou by dou theta of u theta plus dou by dou z of uz. So equal to 0. So that is the continuity equation in the cylindrical coordinates for the incompressible flow problems. So now we will take each term. So first term is 1 by r of dou by dou r of r into ur. So here ur is equal to u into cos theta. So now we are substituting it here, 1 by r into dou by dou r of r into u cos theta. So here u cos theta is a constant. So we are taking it as a constant and it becomes dou r by dou r. So it is 1. So it is u cos theta by r. So I hope it is clear. So what we are doing, we are writing the continuity equation in the cylindrical coordinates, and now we are expanding the each term. That is, we are taking the derivatives in each term and we are just checking whether the continuity equation is getting satisfied or not. So first one is we are taking the equation in the cylindrical coordinates, and first term is 1 by r into dou by dou r of r into ur. So it is 1 by r dou by dou r into u into cos theta. So it becomes 1 by r into u into cos theta, because u cos theta is constant in this equation. Second term is 1 by r of dou by dou theta of u theta. So 1 by r of dou by dou theta of u theta. So u theta is minus of u into sin theta. So 1 by r into dou by dou theta minus of u into sin theta. So again here u is a constant. So now we are taking derivative for sin theta alone. So it becomes dou sin theta by dou theta, which is cos theta. So here it is 1 by r into minus of u into cos theta. Cos theta alone comes from the derivative. U is a constant. And lastly we have dou by dou z of uz. So uz is here w. So dou w by dou z. W here is a constant. So this term becomes 0. So yeah. So substituting back in the original continuity equation, what we will be having, the equation as 1 by r into dou by dou r of r into ur plus 1 by r of dou into u theta by dou t plus dou by dou z of uz equal to 1 by r of u into cos theta minus of 1 by r into u into cos theta plus 0. So these two terms cancel out each other and it becomes 0. So which is the right hand side equation. So now we have proved that continuity equation in cylindrical coordinates is satisfied for the newly transformed velocity components. So that is what was asked in the question. We have proved. So in this, what we need to remember is, we need to remember the continuity equation in the cylindrical coordinates. If we remember the equation, substituting and taking derivatives is not a very it is not a very difficult task, which we can do it easy. The only thing we need to remember is, we need to remember the equation in the cylindrical coordinates as well. So that is for question 4. Now we will go to question 5. So before moving for question 5, we have a simple statement. So this is figure 3, and we are having, consider incompressible flow at a volumetric flow rate Q directed towards a drain. So we have a flow directed towards drain. So drain is here. So we are having a flow and its flow rate, volumetric flow rate is Q. It is directed towards a drain and it is making an angle of theta, that is 45 degree, and that is theta is pi by 4, 45 degree, everything same. With wedge, okay. Consider incompressible flow at a volumetric flow rate Q directed towards a drain at the vertex of 45 degree wedge of width d as shown in figure. So this is the figure. Now all the subsequent problems will have questions based on this particular figure. So now we are just going to see the question 5. If we say that the flow is purely radial, which of the following is correct expression for the velocity profile? So if we say that the flow is purely radial, which of the following is correct expression for the velocity profile? Option A, ur is equal to c by r, u theta is equal to c by r, uz is equal to c by r. Option D, none of the above. So what is given? So when we are saying the flow is purely radial. So what does it mean? So it means that the UR component is varying with respect to radius. That is, UR is varying in the radial direction. So that is what we mean by flow is purely radial. So option A is the right answer. That is, UR is equal to C by R. So C here is some constant. I mean, you can't call it as a constant, some function. Okay, it can be constant. Yeah. So UR is a function of radius, that is here. So UR is equal to C by R. So that is what we mean. So just to prove and validate our answer, let us see some expanded steps. First one, it is given that radial incompressible flow towards a drain located at the origin of a wedge, and angular limits are given from theta is equal to 0 to 45 degree, that is pi by 4. Width of the wedge in the direction perpendicular to the r theta plane is b. Width is given as b. Flow is purely radial. That is, what it means is that UR is equal to I mean U component, sorry, velocity in the R component is a function of R. That is what we mean. So UR is equal to UR as a function of R and U theta equal to 0. And we need to find an expression for the radial velocity profile URR that satisfies the compressible continuity equation. So was it asking the question? So yeah, an incompressible continuity equation. Expression for the velocity profile actually. And if we look at the question, basically what we are asked is correct the expression for the velocity profile. So we'll leave out the rest of the things. Okay. Now it's clear actually. So continuity equation in cylindrical coordinates. So as seen from the last problem itself, we are just rewriting that particular equation. 1 by r into dou by dou r of r into ur plus 1 by r of into dou by dou theta of u theta plus dou by dou z of uz equal to 0. This is the continuity equation in the cylindrical coordinates. So incompressible steady flow in cylindrical coordinates. So this is the equation. So here we have seen that UR is a function of R and U theta is a function of U theta is 0 and there is no variation in the z direction. So the equation becomes such that only this term remains. U theta becomes 0 and uz there is no variation, so these two terms become 0 and we will be left with 1 by r into dou by dou r of r into ur. So this term becomes dou by dou r of r into ur equal to 0. So So now we need to know that, I mean, how we can, when can we say that it is dou by dou r of r into ur equal to 0? R into ur is equal to constant. When r into ur is equal to constant, ur is equal to constant by r. So c is a constant, so it is ur is equal to c by r. So that is the problem. I mean, that is the answer to this particular question, that is question 5. So what we did, we are asked to find ur. I mean, when we say purely radial flow, what was the meaning? It was asked in the question. So we say that if it is ur, I mean purely radial flow, ur is varying with respect to the radial direction and u theta is 0 and there is no variation in the z direction. So we write the continuity equation, we simplify the equation and we get the velocity profile in such a way that ur becomes a function of r. I mean, ur is equal to c by r. C is a constant here. So that is the answer to question 5. Now we'll move on to next question, question 6. So question 6, velocity profile in the previous question will violate which of the following? So the velocity profile in the previous question, that is ur is equal to c by r, u theta 0, u z 0, which will violate which of the following? So options are option A, no penetration boundary conditions on the walls. Option B, equation for incompressibility. Option C, both A and B. Option D, neither A nor B. So answer is option D, that is neither A nor B. So answer is that we will see how option D is the right answer. So what are all the two statements given? The first one was no penetration boundary condition on the walls. So no penetration means fluid should not cross the solid boundary. Normal component of the velocity at the wall must be 0. So if normal component is velocity at the wall is 0, it just means that there is no penetration, that is no crossing of that boundary. That is what it means. So which has a solid wall at theta equal to 0 and theta is equal to pi by 4. So normal direction to the walls is in the theta direction. So u theta is 0 at the wall and u theta is everywhere 0. So it will be 0 near the walls as well. So here it means that no penetration boundary condition is satisfied. So no penetration boundary condition is satisfied. Second one, equation for incompressibility. So when we talk about equations for incompressibility, which we saw in the last problem as well, ur is a function of r and it is equal to c by r. So the reduced incompressibility equation is this 1 by r into dou r of r into ur. So on substituting, we will be having 1 by r into dou r of r into c by r. So r gets cancelled and it will be c. So it is a constant. So it becomes 0. So equation for incompressibility is also satisfied. So both the I'll write it more clearly. So equation for incompressibility is also satisfied. So answer is none of the above, that is neither A nor B. So I hope it is clear now. Now we will go to next question, that is question 7. What is given in question 7? In question 7 it is mentioned that Simplify the viscous term in the R momentum expression and find it as dash. Simplify the viscous term in the R momentum expression and find it as dash. So, answer is, for that first we need to write the equation, Navier-Stokes equation in the R direction. So previously if it is a Cartesian coordinates, we will be writing it in the x, y, z direction. So now the coordinates are r, theta, z in the cylindrical direction. So we need to write the equation in the R, momentum equation in the momentum conservation equation in the R direction, and we will solve it for the viscous terms. So that is mostly that mu into so and so terms, right? Those are the terms. So first let us write the equation in the R momentum direction. So equation is this. Okay. Momentum equation conservation equation in the R direction. Okay, so just a simple thing. I mean, I'll write for here as well. Equation in the z direction. And just two. So momentum conservation equation in the r direction is given by this particular equation, which is nothing but rho into dou u r by dou t plus u r into dou u r by dou r plus u theta by r into dou u r by dou theta minus u theta square by r plus u z into dou u r by dou z. If at all any equations are wrong, please verify with the book. It might be typo when I typed. So just, I mean, answer is right, but if at all I missed out anything, just if you're having any doubts with the equation, just cross check with the valid, I mean, textbook. So I mean, it might not be intentional, but it might be typo. So yeah, equal to minus dou p by dou r plus mu into del square u r minus u r by r square minus 2 by r dou u theta by dou theta. So now del square u r is given by 1 by 1 r of dou by dou r of r into dou u r by dou r plus 1 by r square of dou square u r by dou theta square plus dou square u r by dou z square. So here the whole viscous term is given by this, that is mu into this particular term. So that is 1 by r into dou by dou r of r into dou u r by dou r plus 1 by r square dou square u r by dou theta square plus dou square u r by dou z square minus u r by r square minus 2 by r square into dou u theta by dou theta. So these are the viscous terms in the equation. Terms. So yeah, I mean, I'll just show it in this way, then going into slide show mode. So viscous terms are given by this particular term substituted in here will give us the whole equation. So now ur is equal to c by r, that is a constant by r. So we are just substituting it here in the first term, 1 by r dou by dou r of r into dou u by dou r by r. So it becomes 1 by r of dou by dou r of r into dou c by dou r. So it becomes c is constant, so it comes out 1 by r. 1 by r is minus 1 by r square. So dou by dou r of minus r by c minus r into c by r square, which one r and r gets cancelled. So it is minus c by r. Dou by dou r of minus c by r. So that will become c by r square. 1 by r into c by r square will give us c by r cube. So this is the first equation. So again ur is a function of r. So this term becomes 0. And this term also becomes 0 because ur is a function of r and it is not varying with respect to theta or z. So these two terms become 0. Now again we have u theta and u theta is already 0 which we saw in the previous problem. So we have ur by r square. So that is pending. So now we are taking ur by r square equal to ur is c by r. So c by r square. So it becomes c by r cube minus c by r cube. So it becomes 0. So that is the problem. So now we are asked to find the viscous terms in the r direction. So for that what we did is momentum. We wrote the momentum conservation equation in the r direction. And we identified the viscous terms in the r direction momentum equation. And we wrote them separately. And we substituted ur as a function of c by r. And we did derivative. We took the derivatives. And for all others it became 0. We just substituted back in the equation and it becomes 0. Viscous terms become 0. So that is for the r direction. Now we are going to see for the z momentum expression and find it as dash. So that was in the r direction. Now what if in the question instead of r direction it is asked to find it in the z direction. So simplify the viscous terms in the z momentum expression and find it as dash. So similarly rather than going into thing, we are just going directly and we are seeing the writing the momentum conservation equation in the z direction directly. And this is the cylindrical coordinates that you should be aware of. Rho into dou u z by dou t plus ur into dou u z by dou r plus u theta by r into dou u z by dou theta plus uz into dou u z by dou z equal to minus of dou p by dou z plus mu into del square uz. So we have this particular term alone, viscous terms. Viscous terms is del square uz equal to 1 by r of dou by dou r into dou by dou r of r into dou u z by dou r plus 1 by r square of dou square u z by dou t square plus dou square u z by dou z square. So what we know is u z is a 0 here. So it is all the terms become 0. So this becomes 0, this becomes 0 and this also becomes 0. So viscous terms in the momentum z momentum expression is 0. So that is the conclusion. Yeah. So I hope this particular problem is also clear to you. Now we will go to question 9. Okay, so question 9. We have a problem statement. So we have a water in a tank and we have a pipe at a height of 6 plus 2 meter and we have the diameter of the pipe before and at the exit it is 12 centimeter and 5 centimeter respectively, and 6 meter of water is the height of height below the surface and 2 meter is above the surface. So this is given in the problem statement. Now we will see what is asked in the question. A pump shown in figure draws 250 meter cube per hour of water at room temperature from the reservoir. The total friction head loss is 5 meter. Flow discharges through a nozzle to the atmosphere. So what is given? We are given a pump and it draws 250 meter cube per hour of water at the room temperature from the reservoir. So total friction head loss is 5 meter. So friction head loss is 5 meter, and flow discharges through a nozzle to the atmosphere. So we have a nozzle which discharges the water to the atmosphere. So this is the given in the question. Now we will see what is asked related to this particular statement. So we have question 9. The velocity of the fluid at the surface of the water in the tank can be considered as dash. Velocity of the fluid at the surface of the water in the tank can be considered as dash. Option A 0 meter per second, option B 1 meter per second, option C 2 meter per second, option D 4 meter per second, option E 6 meters per second, option okay. So answer is actually 0 meter per second, because it is mentioned that the velocity, in the question it is asked for the velocity of the fluid at the surface of the water in the tank. So since we are talking about the surface level, we can take it as a 0. So answer is option A, that is 0 meter per second. So to have more idea behind why it is 0, we will just see a quick explanation. So what is given? Water surface is open to the atmosphere. Pump draws water from the large tank. Tank is large and water surface area is generally greater than the pipe cross sectional area. So when we talk about the water surface area, it is larger than the surface area of cross sectional area of the pipe. So we are making one assumption. Since tank is very large, surface area is large compared to the inlet pipe, velocity of the fluid at the surface can be considered negligible. So because of this particular assumption, we are considering the velocity of the fluid at the surface as negligible. So it can be 0. So that is what is the answer to this problem. V surface is 0 meter per second. So that is for the question. Now we will go to question 10. In question 10, what is given is that the exit velocity is dash. So we considered the surface level velocity as 0. So now what is the exit velocity? So now what we need to do is we need to use the Bernoulli equation. So when we use the Bernoulli equation, we will be getting the value. Just a minute. So yeah, we are asked to find the exit velocity and we have to use the Bernoulli equation. So we will see how we get the answer. Options given are option A 40 meter per second, option B 21 meter per second, option C 35.36 meter per second, option D 53.56 meter per second. So the answer is actually option C 35.36 meters per second. So we will see how. So first, as usual, we will write what is given in the problem. So we are given flow rate is 250 meter cube per hour. So we first convert it into meter cube per second. So for that, what we are doing, we are dividing it by 3600, because 1 hour equal to 3600 seconds. So Q is equal to 250 meter cube per hour equal to 250 by 3600 meter cube per second, which is giving us 0.0694 meter cube per second. If there is any small calculation error, kindly adjust, just follow the procedure, that will be good. it won't be to max, but yeah, still if there is any calculation error, please forgive. So exit diameter is given as DE, which is 5 centimeter or 0.05 meter, right? So exit diameter is given and exit flow rate is given. So we are just asked for the exit velocity. So how will we get the exit velocity? In the last week problem itself, we saw that volumetric flow rate is equal to cross sectional area into velocity. So here cross sectional area is for a cylindrical pipe, I mean cross sectional area will be circular area, right? So it is pi by 4 d square. So pi by 4 into dE square, that is pi by 4 into 5 into 5, that is 0.05 square into pi by 4, which will give the cross sectional area at the exit as 0.0019625 meter square, and that is cross sectional area. Now, I mean, it is just applying the continuity equation that Q is equal to A into E, A into V. So, well, volumetric flow rate is equal to area in cross sectional area into velocity at the exit. So, velocity at the exit will be cross section volumetric flow rate divided by the cross sectional area. So, volumetric flow rate is 0.0694 divided by cross sectional area is 0.0019625. So that will give us the exit velocity as 35.36 meter per second. So that is the answer. So what we haven't done anything big, what we did is we just substituted in the formula, that is V equal to Q by A. So and then we got the answer. So I hope it is clear. Now we will go to next question. The pump head in meter I was just mentioning we will be using Bernoulli equation, right, for the previous question. We need not use because it was a very straightforward problem, so we need not use, but in this particular problem we will be using anyway. The pump head in meter can be obtained as dash. So what is given in the question? It is given that the exit flow rate is given, that is 250 meter cube per hour. 250 by 3600 will give us 0.0694 meter cube per second divided by 3600, 0.0694. And inlet free surface of the tank, that is at 0.1, and outlet is nozzle exit, that is 0.2. Elevation difference, that is between height, if we take inlet as 1 and outlet as 2, Z2 minus Z1 will be 8 meters. If you remember, immersed water height is 6 meter, and above the surface it is elevated at a 2 meter height. So 6 plus 2, it is 8 meters. So friction loss is given in the question as 5 meters. And velocity at the surface, we assumed it as 0. Velocity at the exit nozzle, we calculated it as 35.36 meter per second. Atmospheric pressure is at both the points P1 and P2. So now we can use the formula Bernoulli equation with pump head and head loss. So P1 by rho g plus V1 square by 2g plus Z1 plus HP equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. So now we are substituting everything we know back into the equation, and we will be getting HP answer. So HP will be 76.73 meters. So HP we got it as 76.73 meters, that is the pump head. Now in the next question what we will be doing is we will be asking to estimate the pump power in kilowatts delivered to the water. So pump power in kilowatts is asked, so it is pumping power required for delivering the water is given by rho into G into H into Q. So rho is the density of water, G is the gravitation, Q is the volumetric flow rate, HP is the pump head. So now everything is very straightforward. We are just substituting everything back over here. So 1000 into 9.81 into 250 by 3600, that is meter cube per second, into pump head in 76.73. so after substituting everything, we will be getting the value as 52,272.3 watts, and in the question it is mentioned that pump power estimation is required in kilowatts. So we are just dividing it by 1000 and using the kilowatts unit, which is nothing but P is equal to 52 kilowatts, 52.27 kilowatts. So that is for question 12. Now we will go to question 13. So these few problems we will again see in the different numerics in the last 2-3 problems. So that's why I am just jumping it quite fast. So yeah, for question 13, uh, just we'll just take a 5 minutes break. Uh, 4:17 now. We'll get back by 4:21. Thank you. Okay, I think we can start. Question 13 it is. And R cap equal to dash into x cap plus dash into y cap. So option A minus cos theta into x cap plus sin theta into y cap. Option B minus cos theta into x cap minus sin theta into y cap. Option C cos theta into x cap plus sin theta into y cap. Option D cos theta into x cap minus sin theta into y cap. So answer is actually option C cos theta into x cap plus y sin theta into y cap, or r equal to x cos theta plus y sin theta. We used to do that, right? So this is just that form only. So question 13 is a simple form. R is equal to x cos theta into, sorry, r is equal to x cos theta plus y sin theta. So r cap is equal to x cap cos theta plus y cap sin theta. So straightforward problem. And yeah. Okay, we have five more problems. So these five problems are kind of repetition of what we have seen in the previous problems. So I think it will just brush up what are all the things we have learned in today's class, and also with the different numerics it will be helpful. So what is asked in the question? We'll just read the question. A block of weight W slides down an inclined plane while lubricated by a thin film of oil as shown in figure 1. The film contact area is A and its thickness is h. Assuming a linear velocity distribution in the film, derive an expression for terminal velocity v of the block. Find the terminal velocity of the block if the mass of the block is 7 kg, A equal to 45 cm square, theta is equal to 15 degree, and the film is 0.5 mm thick, oil of viscosity 0.33 kg per meter second, and density 900 kg per meter cube. Report the answer in meter per second. So it is the same problem as in the previous question. So what are all the things different is, in the previous problem we are asked to find the inclination angle. In here we are asked to find the terminal velocity of the block. So let us quickly brush over what is given in the question. So what is given? We are given a block of weight W and it is sliding down the plane which is at an inclination of okay, it is basically not the 15-degree inclination, inclinated at an angle. Okay. There I changed the question but I forgot to change here. That's it. And, all these problems are similar to what is given in this week's assignment and practice problems. In addition to the assignment problems, you are also given few set of practice problems. So I took those problems and modified the question slightly, either in terms of what is being asked or in terms of numerics, so that it will be like very easy for you to submit the assignments. So that is the thing. So that is the confusion why I am changing few numbers. So due to that reason, some problems might be looking like a physically unfeasible one because of changing few numbers. So but yeah, as I mentioned earlier, don't take numbers into picture in these problems. Just look at the concept of how it is solved and what it is implying. So that will be more easier. So again, yeah, when we talk about the question here, the inclination angle is given as 31 degree and the film thickness is 0.5 mm, and oil, that is the lubricating oil, its density is 900 kg per meter cube and its viscosity is 0.33 kg per meter second. So when we are coming to the block, its mass is 7 kg, area is 45 centimeter square, and we are asked to find its terminal velocity. So we will go to the answer. What is given? We are given a block of weight W and it is sliding down an inclined plane while lubricated by a thin film of oil. Lubrication is resisting the motion due to viscous shear. And the mass of the block is given as 7 kgs, and the area, that is the contact area between the block and the film, is given as 45 centimeter square, or it is 45 into 10 power minus 4 meter square. And film thickness is very thin film, so it is 0.5 mm or zero point 0.5 into 10 power minus 3 meter. So as we have seen, we are maintaining the unit consistency throughout the problem. So we are just converting everything into SI units where mass is in kgs, uh, length is in meters, and time is in seconds. And viscosity of the oil is 0.33 kg per meter second. Density of oil is 900 kg per meter cube. And G is 9.81 meter per second square. Inclination angle is 31 degree. So now what we are asked to find? We are asked to find the terminal velocity. So first, how will we get the solution? So first we will be doing the force balance as we did in the previous problem. So how are we balancing? We are balancing the gravitational force and the shear force, viscous shear force. So gravitational force is F is equal to m into gx, or F is equal to m into g into sine theta. And viscous shear force is given by F is equal to tau into A. So tau is equal to F by A. Sorry. Tau is equal to F by A. So F is equal to tau into A. So tau is mu into dv by dx, because we are given a linear velocity distribution across the film. So it is dv by dx, or v by h as given in this problem. Shear stress is equal to tau equal to mu into v divided by h. So v here is the terminal velocity and h is the thickness of the film and mu is the viscosity of the oil. So we are substituting this expression in the viscous force expression, and we will be getting viscous force as mu into v by h into a. Now we are substituting it back in this particular equation. So at terminal velocity, net force becomes 0. So mg sine theta equal to mu into v by h into a. So in this we know m 7 kg, g we know, theta we know, mu we know, v is unknown and h is known, a is known. So we are just substituting back. So mg sine theta is equal to mu into v by h into a. And what v will be? V is equal to, we are taking rest of the terms to the other side. So v is equal to mg sine theta into h. H is denominator, so it goes to the numerator. H divided by mu into a. Whichever are in numerator here are going to the denominator. So v is equal to m into g into sine theta into h by mu a. So sine theta is equal to sine theta sine 31 degree equal to 0.52. Excuse me. I'll just check once. Sine 31. It is 0.515 or 0.52. So E is equal to mg sin theta into h by mu a. So sin theta is sin 31 degree, it is 0.52. So we are substituting everything back in the equation. So v is equal to 7 kg into 9.81 into 0.52 into 0.5 into 10 power minus 3. H is 0.5 mm, so that one divided by mu, that is 0.33 into 45 into 10 power minus 4. A is 45 into 10 power minus 4. So V equal to 12.02 meters per second. So on substituting everything, we will be getting this answer. 7 into 9.81 into 0.52 into 0.5 into 10 power minus 3 divided by 0.33 into divided by 45 into 10 power. It is 12.02 meters per second. So that is the answer. In the previous question, velocity was given as 12 meter per second, and we were asked to find the theta. So similar thing we are doing it here also. So yeah, now we are going to this pump problem. As I mentioned while doing the pump problem itself, we will be dealing with a different numerics. So that's why I moved fast over there. So here again, we will see the statement first. A pump shown in figure 6, this is that particular figure, draws 400 meter cube per hour of water at room temperature from the reservoir. The total friction head loss is 10 meters. Flow discharge through a nozzle to the atmosphere. So what is given? Shown in figure 6 draws 400 meter cube of water at room temperature from the reservoir. So the total friction head loss is 10 meters and flow discharge through a nozzle to the atmosphere. So here again pump is giving out water at VE is equal to exit velocity is VE, exit pipe diameter is DE and it is 5 centimeter, and D is 12 centimeter, and it is 2 meter height above the surface and 6 meter above below the water. So pump is withdrawing 400 meter cube of water at room temperature. So we need to calculate the things. So we'll move to the question. In question, it is given that the velocity of the fluid at the surface of the water in the tank can be considered as dash. So again, it is Q is equal to A into E. Sorry, A into V. V is equal to Q by A. That is the problem. So now if we do it with that, options are option. Okay, sorry, it is not at the exit, it is asked at the surface of the water in the tank. So velocity of the fluid at the surface of the water in the tank can be considered as option A 0 meter per second, option B 1 meter per second, option C 2 meter per second, option D 4 meter per second, option E 6 meter per second. So answer we know is option A, that is 0 meter per second is the right answer. Why? Because water surface is open to the atmosphere. Pump draws water from the large tank. Tank is large and the water surface area is significantly greater than the pipe cross sectional area. So we are having the assumption that since the tank is large and the surface area is large compared to the pipe, inlet pipe, velocity of the fluid at the surface can be considered negligible. Based on that assumption, we are giving the velocity at the surface as 0 meter per second. In question 16, moving on to question 16, what is being asked? In question 16, it is asked that exit velocity is dash. Option A 0 meter per second. Option B Option B 1 meter per second. Option C 6 meter per second. Option D 14.1 meter per second. Option E 24.1 meter per second. Option F 34.1 meters per second. Option G 44.1 meters per second. So answer is option F 34.1 meter per second. So how it is? Q is equal to Q 400 meter cube per hour is given in the question, and we are converting the meter cube per hour into meter cube per second. So 400 divided by 3600 gives us 0.111 meter cube per second, and exit diameter is mentioned as 5 centimeter. Cross sectional area at the exit is pi by 4 d square. So it is pi by 4 into 0.05 square, which gives us the cross sectional area at the exit as 0.0019625 meter square, and we are applying that Q is equal to A into V. So V becomes Q by A. So Q here is 0.1111 meter cube per second divided by 0.0019625, which gives us 56.62 meter per second. So now I hope it is clear. Now we will see question 17. The pump head in meter can be obtained as dash. So pump head in meter is asked. Flow rate is given as 400 meter cube per hour, or 400 divided by 3600 meter cube per second, which is 0.11 meter cube per second. Inlet is the free surface of the tank at point 1. Outlet is the nozzle exit at point 2. Elevation difference is again Z2 minus Z1 is 8 meter. Friction loss is actually 10 meter, not 5 meter. I just copied it. Friction loss is given as 10 meters, right? Friction head loss is 10 meters. V1 velocity at the surface is 0 and V2 is 56.62 meter per second. So atmospheric pressure at both the points. So now we are applying the extended Bernoulli equation with pump head and head loss included. This is 10. This will be 181. Okay. Just a minute. I'll just check once with the calculation. I have a small doubt over here. G H rho G H. So basically, I have one doubt in this particular problem regarding taking the height elevation difference. So I am, I am having a small doubt over here, which I will clarify while uploading the presentation. I'll check after the class. But I think by using this, it might be slightly wrong, which I will clarify it while uploading the PPT. Just check it over there before you are using it for your assignments. But anyways, I mean, this Z2 minus Z1 alone, I have a doubt. The rest is fine. So P1 by rho g plus V1 square by 2g plus Z1 plus HP is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. So we are substituting everything, and we will be getting the HP as 181.4 meter. So that is the thing. Z2 minus Z1 alone, I'll confirm it after this class. Okay. So the last problem for today's session, it is question 18. Estimate the pump power in kilowatts delivered to the water. So again, pump power is given by rho g h into q. So rho g is, as we know, rho is the density of water and g is the gravitational acceleration due to gravity, and q is the flow rate. HP is pump head. So it is 1000 into 9.81 into 400 divided by 3600 into 176.40. On substituting all the numerical values, we will be getting the answer as 190 to 276 watts. So in kilowatt, it will be like 192.2 kilowatts. So that is the thing. 92.28 kilowatts. So yeah, thank you for this session. So if you have any doubts, you can ask me. Question 17 and similar problem, the pump head calculation where we applied the Bernoulli equation, right? This question 17 and also similar question which we did in here. This one. I have a small doubt. Question 11 and question 17. I'll just verify it once again, and while uploading the PPT, I'll upload the correct one. Yeah. Apart from that, if you have any doubts, you can ask now. Thank you. Then we'll again meet next week at the same time. That is 3 p.m. to 5 p.m. and we'll discuss the problems. Thank you. Okay, just a small clarification which I want to give here in problem 11, and where we are substituting in the elevation. I mentioned one thing wrong in this problem. As I was saying, I'll correct it and upload it later. So I just found out the error. Z2 minus Z1. So point 1 is free surface. So Z2 minus Z1 is 2 meters. It is not 8 meters. So we need to use it as 2 meters. So Z2 minus Z1 is 2 meters. Again, it is 2 meters. 70.73. So it is 70.73. 63.73 plus 5 plus 2. 70.73. I hope it is clear. I'll just come back once again. Again, here it is 2. Here it is, instead of it is 2. 165, 175. Okay. I'll explain somewhat clearly now. We'll go to question 14. So we are asked to find the pump head in meters. So what we are doing, we are taking the point 1 as free surface of the reservoir and point 2 is at a exit of the nozzle exit of the reservoir. So between point 2 and point 1, if we look at the figure carefully, it is point 2 and point 1, it is 2 meter, it is not 6 meter. We are not taking the pressure at this point, we are taking it as open to the atmosphere, so it is 2 meters. So by using that, what we are doing, pump head in meter, we are calculating outlet is nozzle exit point 2, elevation difference is Z2 minus Z1, so it becomes 2 now, and friction loss remains 5 meter. Velocity at the surface V1 is equal to 0 and velocity at the nozzle V2 is equal to 35.36 meter per second. And atmospheric pressure is gauge pressure because it is open to atmosphere. Now it becomes correct. Previously we should have taken it at the bottom, but we didn't do that. So formula is extended Bernoulli equation with pump head. So it is, now we are substituting everything, and Z2 minus Z1 is now 2 meters and HP is 63.73 plus 5 plus 2. Now it becomes 70.73 meter. So this one is the right approach. And similarly in the last problem, that is 18th question, we did a mistake over there as well. A pump shown in figure 6 draws 400 meter cube of water and the total friction head is, now we are asked to find the pump head. It was in 17th or 18th question. So Z2 minus Z1 elevation difference, again here it is 2 meter, it is not 6 meter. So V1 is this, V2 is this, P1, P2 is gauge pressure, and we are substituting Z2 minus Z1 as 2 meter and we are getting the, I mean everything else is same as how we did before. Only thing is Z2 minus Z1 is 2 meter. It is not 6. We should not consider the 6 meter below the water surface. HP is 163.4 plus 10 plus 2 and it is 175.4 meters. So that is the right answer. So again, if it is 170, how will it be 175.4? Yeah, it is 175.4. 1000 into 9.81 into 400 into 175.4 divided by 3600, 186. So it is 191.19 kilowatts. So pump power also varies depending on the pump head. Pump power also varies. In question 12 also there is a small change again because of the variation in the pump head. 70.73, 70.73. Now we should substitute 70.73 here. So 1000 into 9.81 into 250 divided by 3600 into 70.73. 48,184. or 48.18 kilowatts. So these are the two changes. We calculated the height difference wrong, so we changed it into a proper height difference and calculated the pump head, and because pump head got changed, pump power also got changed. So these are the two things, and because of the two problems got changed slightly. So yeah, that's it for today's class. Thank you everyone for attending today's session. We will meet again at next week, same timing from 3 p.m. to 5 p.m. on Saturday. Yeah, thank you so much. I'm closing the session. Thank you.